In our next example, this is our second example of a contradiction. I want to prove that log base 2 of 3 is irrational. And so what we're going to do is for our proof, we'll assume for a contradiction. This is how I'll start to say it, but assume come on, pen. Assume for a contradiction that log base 2 of 3 is rational. That means that then what we can say is that then there exist integers. So then there exist integers a and b, so that log base 2 of 3 equals a over b. And then I just want to remember what log base 2 of 3 is. Notice that 2 and 3 are both positive numbers. And just in general, I think this is worth writing down. If I have log base b of x equals y, that's by definition of what a log is, saying that b to the y equals x. Okay, so in other words, y, being this log, is exactly the power that you have to raise b to get x. So that's what a log is. And if we think about, we're trying to solve 2 to the x equals 3, or if you want to call it 2 to the y. Let me not use x and y because I just used them in the previous step, but we're trying to find 2 to the t equals 3. And so log base 2 of 3 has to be greater than 1. So notice that t has to be greater than 1 because 2 to the 2, I'm sorry, 2 to the 1 is 2. And so 2 to the t is an increasing function. So if we want 2 to the t to be equal to 3, which is bigger than 2, we need a larger value because the function's increasing. So in particular, a and b are not 0. Okay, b can't be 0 anyways because it's in the denominator. But actually, you can say a little bit more. So let me add that in, little iPad magic. Not only do there exist integers, a and b, but there exist positive integers. Okay, so we can add in a little bit more there. So there exist positive integers, a and b, so that log base 2 of 3 is a over b. And so again, by definition, just going back to what we mean when we say something's the log of something, we can conclude that 2 to the a over b is equal to 3, because that's what, just by definition of a log, that's what that means. And therefore, if we raise both sides to the bth power, we have 2 to the a equals 3 to the b. And so now we need to find a contradiction. And it turns out that if a and b are positive, then the left side is always even, and the right side is always odd. Okay, so since a and b are positive integers, it follows that 2 to the a is even for all a. That's not an obvious statement. Obvious is a 4-letter word in math. But you should prove this, and I'd like you to prove it. How can you prove that 2 to the a is even for all a? What I've said is false. But for all integers a greater than or equal to 1, right? It's not true if a is 0, for example, but it is true for all integers greater than or equal to 1. You could prove this by induction. You could prove this lots of ways, actually. So induction might be a little overkill here, but there's something to prove here, and so you should do that. I'm actually going to leave this part of the proof blank, as it were, so you can fill in. And then likewise, 3 is odd, so 3 to the b is odd for all integers b greater than or equal to 1. Okay, so if you take an integer and you, again, you could do this by induction if you want. There's a few other things that you could do here. Yeah, but 3 to the b is odd for all integers b. So you should be able to prove these. So I'm just going to put little red stars here. Try and prove those on your own. Prove that 2 to the a is even for all integers a greater than or equal to 1, and 3 to the b is odd if b is greater than or equal to 1 for an integer. So given that, what's our contradiction? Well, the contradiction is that you can't have a number be both even and odd, right? So even and odd numbers have different forms. So since 2 to the a equals 3 to the b, and yet 2 to the b is even, I'm sorry, 2 to the a, just be consistent with myself, is even, and 3 to the b is odd, there's our contradiction. Okay, so the contradiction is that they can't really be equal. If one's even, one's odd, they can't be equal. So we have a contradiction. I want to point out it doesn't make a difference at all what the contradiction is that we find. All that matters is that our assumption contradicts something. And if that happens, then our assumption couldn't be true, and therefore we win. Okay, so in our case, we assumed for no good reason that log raised 2 of 3 was rational. It turns out that that can't be the case, because that would imply that there's a number that's both even and odd, which we know can't happen. And that means that our starting assumption must have been wrong. Okay, it can't be that log base 2 of 3 is rational. So the only thing that we can say, the only way we can go from here is that all we can conclude is that log base 2 of 3 is irrational. Okay, so that's enough to prove that log base 2 of 3 is irrational.